So it's already 7, but we'll wait for 10 more minutes as no one else has joined. So let's wait for 10 more minutes until some people joins at least. I think we should start with today's problem solving session. So, first of all, let's revisit what Sir taught on class. So, first of all, what he taught on class was that there is a viscometer where some fluid is present in between two circular cross sections, like one is the inner one is we can move, and the outer one is static, like this. So I won't go to the whole derivation, but I'll just give a brief idea like what Sir taught, so that we can understand what we are going on to do in the class. So the inner one is moving with angular velocity, and there is one fluid having viscosity mu in between. So what is happening? This distance from the inner center, we are taking as r, and this the inner radius is r1 and outer radius is r2. Simply, nothing else. So what Sir took? Sir took an elementary cross section in between. So what will happen? Uh, there will be a shaft in middle, and it will be rotating. So what will happen? The inner wall will be rotating with an angular speed omega, and the outer wall will be stationary. So the fluid will be moving with an angular velocity omega, and then it will gradually become steady and will be zero because of no slip condition at the outer wall. So, because of this, there will be one shear stress because of the motion of the fluid generated. So that shear stress, for keeping in equilibrium, the inner shaft should exhibit some force that will be just equal and opposite to the force that is being produced by the shear stress. So this is force into with respect to the shear stress, that will be force into area. So what is the area? See, the shear stress, change in shear stress will be taking place with respect to the elementary cross section. That means if the L is the length of the cylinder, so 2 pi r into L. So 2 pi RL will be the area through which the change in shear stress will take place. Right? And if you will find the moment is equal to this force, that means tau means mu minus mu du dr 2 pi r L into r. R is the radius about which we will be applying that moment, right? So this we are just finding out, and why this is minus, cause as the radius will increase, as we can see, as the radius will increase, the velocity will be decreasing and will gradually become zero at the static wall on outside. Okay, so what is happening, this moment, like Sir have derived this moment equation, so it will become 2 pi mu L omega r1 square r2 upon r2 minus r1. See, done. And sorry. So in terms of omega also, if you assume that okay, so if you assume that this gap between two cylinder, pardon my drawing, so it's not so good. So if this gap between the two cylinders is very small, then we can consider the profile to be linear.
So if the profile is considered to be linear, then also he derive one moment, that will be mu omega r1 upon r2 minus r1 2 pi r1 L r1, right? This will be if the profile will be linear. Uh, then okay, then this derivation is done. I won't go to the much detail of the derivation. I'll just give you a brief idea of this. Then he went for another rotational motion where what is happening, a shaft is there, a plate is there, rather a circular plate that is being rotated, and there is a static wall and there is a fluid in between. So for that also he calculated the moment. This will be similar, the force into area, and sorry, force equal to stress into area, and that force multiplied by the rotation, the elementary volume we are elementary area we are considering, that elementary area, and the distance from the center, that is the moment of like the axis of rotation. From the axis of rotation, what is the distance of that elementary area, that will be the like that will be multiplied with force to get the moment. Okay, done. So let's revisit what is surface tension. So you're understanding, right?
Yes, ma'am.
Okay, then. Surface tension is basically, as sir have told, it is actually coefficient, not a like we are considering it as a force in like it is a force that is generated, like if let's suppose a water is there, like a container is there, a water is there. So if a molecule is present here, it will be experiencing force in all direction because of the other water molecules that are present. This force generated, it will be generated on the top molecules as well. Let me use some other color, then it will be clear. See, if a molecule is present here, then it will also be experiencing force in all direction. But because of the force on, like there is no molecule present on the layer above it, so what is happening, this force remain unbalanced, this force. So this will in turn give rise to the surface tension force. So that is basically a coefficient, that is force per unit area. So it is denoted as Newton per meter. Its unit is Newton per meter. So if we take a drop over here, so the surface tension force in the, this is angle theta, in this direction it is sigma, this is liquid, and this is vapor, and this is solid, this is sigma LV, right? And in this direction this is sigma SL, and this is sigma SV, right? So he also derived that cos theta. That means this, we'll just do the balance. This plus this cos theta is equal to this. So from there we can get the cos theta. Cos theta is equal to sigma SV minus sigma LS or SL, anything, sigma LV. So this will give the contact angle. Now Mm, he also this is basically what, this is basically the Young's equation. This is the derivation of Young's equation that you will be using for any like for any surface. It is valid until and unless that surface is very plain. Okay. Sorry. uh, Now what is happening when if a surface is getting stretched? So if you remember, like this was a surface whose this is the distance from the surface. If we consider this surface to be A, B, C and D, and if we expand the surface, if we expand the surface, uh, this is the distance between the like if we expand the surface, like if from center to center we are taking, then this distance is delta z, like it is expanded in z direction. This is x plus del x, this was x and this was y, and this is y plus del y, and this is the radius of curvature r1. So from similarity, from similarity of these two, we can say that r1 upon r1 plus del z is equal to x upon x plus del x. So r1 and also r1 upon del z is equal to x plus del x, x upon del x. Now what stretches it? So there must be some there will be one pressure difference between the inner and outer surface. Like a liquid is there, a liquid drop is there. It will be in equilibrium as long as the inner pressure and outer pressure, there will be there is a difference between both of these pressures. So because as sir have taught you in the class also, like if this is the surface tension for the water drop, like in this direction surface tension will take place. So this is the inner pressure and this is the outer pressure. So already there is surface tension force in this direction. So this force, that is the force in the outward direction, should be larger than the force in the inward direction, so that this drop remains in equilibrium, right? So this pressure difference sir have given as delta p, and he have derived the expression for this as del p is equal to sigma 1 upon r1 plus 1 upon r2. We will revisit this derivation. I will show you in detail, let's do it now only. So what is happening? This delta p is working on this surface. Just one second. This surface, right? So the area of this surface is xy. So the force that is taking place on this surface is delta p, that is the pressure difference, into area. So delta p into xy is the force that is taking place on this surface. This contributes to the surface energy. So work done associated with stretching of the surface. What is the work done that is associated with the stretching of the surface? So that is equal to sigma, that is the surface tension force, into x plus del x, y plus del y. Work done means force into displacement, right? So if we will do unit balance, this is exactly matching. Why? Because surface tension is force per unit distance. So multiplied by one distance and multiplied by another distance, that is meter square. So that's why we are getting what? Distance, sorry, Newton meter. That is the unit of work. This is the new surface, and minus xy, that was the old surface. So the work done because of the surface tension, that is only helping for the stretching, right? So the surface, so this, if we will solve, we will get x del y plus y del x. Now equating these two, like p del p xy and xy and del z. Del z is the total work done. This is the force and this is the work done. Multiplied by del x is the work done. So we will equate both of them. So del p xy del z is equal to sigma x del y plus y del x. So this will be del p is equal to sigma del z del x upon x plus del y upon y. So x upon del x is equal to r1 upon del z, and del p is equal to sigma 1 upon r1 plus 1 upon r2. So this is the derivation. This is the radius of curvature, both radius of curvatures. Now if it is a liquid drop, like inside there is liquid and outer there is vapor. So if it is like that, then For this, both of the radius of curvatures are equal. So delta P is equal to 2 sigma upon R. And if it is a spherical bubble, bubble means this is liquid, this is vapor, and this is vapor. So there are two surfaces. So there are two surfaces means delta P will be twice sigma by R, that means 4 sigma by R. So if there is an interface and there is a pressure difference across that interface, then how to relate the surface tension to the pressure difference? For that we can use this method. And then he told about this, like this thing what I explained, this, like there is already, if this is the layer of the liquid or vapor, whatever may be, liquid or bubble, whatever may be, this is direction where the surface tension will be acting. This is the PV and this is the inner pressure PL. So PL obviously will be greater than PV to maintain the equilibrium. So this is done. Then he explained about capillary. So what did he say? That there are two type of forces: adhesion and cohesion. So what is happening? Adhesion means on the first class I told you about adhesion and cohesion. That is the interaction or the liking between similar kind of molecules. That is, like molecules is cohesion, and the attraction or attractive forces between the unlike kind of molecules is adhesion. That means if a water is because of capillary, it is climbing up a capillary tube, then the attractive forces between the water molecules itself is because of the adhesive cohesive force, and between the water and the glass, the attractive forces between them is called the adhesive force. Because in case of water and glass combination, the adhesive force is far greater as compared to the cohesive force. That's why in a capillary, when we place in a bath, a capillary tube, when we place in bath, the water will rise. That means the level of the water in the capillary tube will be more as compared to the outer surface. Like height will be more. This is called capillary rise. So this only he explained, right? He derived what? So there is a capillary tube inside, and it has raised up to a height h from this center, and this is the radius r, and these have rise. Now over here what is happening again, this is the surface tension. So this surface tension with angle with the capillary wall is theta. This is radius r. This is the pressure that is on the vapor side, and this is the pressure on the liquid side. And just one second, sorry. And this angle is also theta, right? And this is the radius radius of the meniscus, and this is obviously the radius of the capillary. So we can relate small r is equal to capital R upon cos theta, right? Now we know that delta P we have derived earlier is equal to sigma upon 1 upon R1 plus 1 upon R2. Can you tell me whether here PV is larger, or the pressure in the vapor side is larger, or pressure in the liquid side is larger? I already told you how to calculate. Like,
Vapor side is larger.
yeah. So so del P will be 2 sigma by R, cause it is only one layer and it is liquid. So if it is 2 sigma by R, now sigma is have formed angle theta with the surface of the capillary. So this will be sigma cos theta upon R. So now delta P is equal to P atmospheric pressure minus P liquid. This is equal to rho GH, like a simple hydrodynamic law. So rho GH is equal to 2 sigma cos theta by R. From here we can find H is equal to 2 sigma cos theta by rho GR. Okay, there will be capillary fall also, like if we will place mercury and a capillary glass capillary tube over here, it will be like this. There will be capillary fall because the cohesive force between the mercury molecules is more as compared to the adhesive force between the mercury molecule and the wall. Okay. Then he gave some examples and then he told about fluid statics where the manometer concepts come. Should I go on to the details of fluid statics or have you understood that?
Understood, ma'am. Ma'am, regarding surface tension,
Hmm.
uh, one doubt is there, ma'am.
Yes, yes, tell me.
Like, if there is a question that calculate work for stretching of fluid element,
Hmm.
so that time we take sigma into change of area.
Hmm.
So, well, should I multiply it by 2 or that's it for getting work
Which
done?
I'm unable to understand. Which question you are telling? Like what
No,
the
not this general question, ma'am. If like if
okay.
there is a question
Yes. Tell me.
like calculate the work done in stretching of fluid element,
Hmm.
like in a rectangular frame and all.
Hmm. Hmm.
So that time it will be like sigma surface tension into change of area.
Hmm.
So should I multiply by 2 there?
Yes, if there will be two surfaces, then only you will multiply by two.
If there's a rectangular frame,
If
then
there
it
is
will
a
be 2.
rectangular flame, then there should be two surfaces only. Because in this side there will be one surface, like uh, the fluid inside will form a layer with the uh, rectangular frame, right? So there will be movable rectangular frame. So it will be in like there will be this side and that side. So there will be two sides. So you have to multiply by two in order to find out the work done.
Okay, ma'am.
Because if there is only one side and other is closed, then you wouldn't have to multiply. But since there are two surfaces of the liquid, you have to multiply by two. Because in that case, like if this is the movable handle and this is the liquid, see, let's suppose this is the liquid, then if I give you the top view, this is the handle, then this will be the surface tension on this side and that this is the surface tension on the other side of the frame. So there will be two surface tensions, so multiply by 2. Understood?
Yes, ma'am. Got it, ma'am. Thank you, ma'am.
Let's move on to the questions today. Okay. uh this only, like, just 1 second.
Okay. So I'll move to the first question. Whatever you said, that concept only is applied here. Okay. So can you find this out? Like there is a movable wire and there is liquid inside. So we can see na, there are two surfaces of the liquid. There, the red dots, as you can see. Let's wait for 1 second. So as we can see here, uh, so here, which I have marked the area. So there only we can see there are two dots. So there are two surfaces. So what is happening? The surface tension of the liquid is to be measured. We need to measure the surface tension with a U-shaped wire frame of 8 centimeter long movable side. If the force needed to move the wire is 24 millinewton, then determine the surface tension of the liquid in air. So this is the movable side of the frame, and with this help the we need to keep this in equilibrium. So obviously the force that is been experienced, that will be countered by the surface tension force. So at equilibrium, this both of the forces will be equal. So it said that the force needed to move the wire is 24 millinewton. So we have to determine the surface tension. Can you do that?
We'll try, ma'am.
Yes, yes. I'm waiting. You solve it. I'll come in 1 minute. You solve.
Hello? Have you done it?
0.15, ma'am.
Yeah, correct. So let's solve it for now. So the force balanced on the liquid film is in contact with the wire. So let's draw that first. So if this is the wire, this is the force that will be generated on both sides. And this is the force that is experienced on the opposite side to keep to extend the film. So this is the liquid film. This is the wire. So what is happening? The force required to keep this movable film at equilibrium, as I already told you, is 24 millinewton, right? So we have to find the surface tension. So force surface tension will be is equal to that force, right? So surface tension into the surface tension is basically, as I told you, it is just a coefficient. So surface tension is equal to Newton per meter. So we'll just multiply it with meter, nothing else. So meter is the length, length that is been. If we think that length is L, so it is already given here. So and there are, since there are two surfaces, so we'll multiply it by 2. So gamma will be F upon 2L. So L is given as 8, I guess. 1 second. So yes, 8 centimeter long movable side. So over this whole wire, the surface tension force will be acting at every point. So this will be L. So 2 into 8 into L is in centimeter. So we will just convert it to meter, 10 to the power minus 2. And force is 24 into 10 to the power minus 3 milli. So we'll convert into Newton. So it will be 0.15 Newton per meter. So this is option C. Let's move to the next question then. A capillary tube is inserted in mercury, kept in an open container. The mercury level inside the tube shall rise above the level of mercury outside, obviously, or the cohesive force between the molecules of mercury is greater than the adhesive force between the mercury and glass. So what is happening? Tell me, like which of them are true? Which of the both of the sentences? Is one true, or a true, or the reason is true, or both of them are true? Tell me.
A is false, R is true.
Yeah, correct. So as we told you, like this is the mercury, and if this is the outer layer, it will be depressed, not rise. So capillary rise won't take place, the depression will take place. So this is done. Now let's move to question number 3. When the pressure on a given mass of liquid is increased from 3 megapascal to 3.5 megapascal, the density of the liquid increases from 500 kg per meter cube to 501 kg per meter cube, while the temperature of the liquid remains same. What is the average value of the bulk modulus? Simply the bulk modulus formula will apply, nothing else. Do you remember the bulk modulus formula?
Change in pressure to volumetric strain.
Yeah, change in pressure to volumetric strain, but for density, like it will be negative for that case. For density, it will be just like delta density upon the initial density, right? So do that. For density change, it will be positive, because when will increase the pressure, the density will be increasing.
250 MPa.
Yeah, correct. Mm. Okay, so let's do it now. Bulk modulus equal to density dp by d rho, actually d rho upon rho in the denominator. So if this is 500, the initial density, 3.5 minus 3 upon 501 minus 500. So this is 250 megapascal. So this is option B. Okay. So the water in a tank is pressurized by air at the top of it, and the pressure is measured by a multi-fluid manometer, as we can see in the figure. The tank is located on a mountain at an altitude of 1400 meter, where the atmospheric pressure is 85.6 kilopascal. Okay, so the atmospheric pressure is given. So the pressure at point 2 is given. Okay, so if I consider this is the enclosed space, oh, pardon my drawing. So okay, so if this is, let's suppose, point 2, this is, let's suppose, point 3, and this is point 4. This difference is H2, this difference is H3 and this is the layer, and this difference is H1. Okay, so this is point 1, let's suppose this is point 4, this is point 3, and this is point 2. This is water, this is closed, this is air. So what is happening? At this point, at point 2, we know that the atmospheric pressure is given as 85.6 kilopascal. So H1, H2 and H3, everything is given. Density is also given. So we have to find the air pressure in the tank. That is, we have to find the pressure at point 1, P1. Can you solve this?
Will try, ma'am.
Yeah. I'm here only. Tell me if you face any problem. If you will solve, then please tell me, okay? Hello?
Just a minute, ma'am.
Yeah, yeah, sure. When you solve, you'll tell.
Ma'am, getting 130 kilopascal.
130, 130. So it's very easy. Let me explain it for you. How have you found out? See, we'll always try to find the unknown in respect of known. So here known was the pressure at point 2, right? Have you found out in that way?
Yes, ma'am. Like from 2 point, I went to air side.
Correct. So let's do it once more. So here P3 will be P2 plus density of what is there at point 2? It is water, mercury, right? Mercury. So mercury G into H3. So this is 85.6 This is 136.00 and 9.81 and H3 is 0.35. So this will sum up to 132.295.6. Now we'll go for P4. P4 means here. So P4 is above to P3. So we'll just minus. So that's hydrostatic height will be getting will get negated. So P3 minus rho, here it is oil, right? Oil GH2. So this is 132295.6 minus density of oil. What is density of oil? 850 into 9.81 into zero point 0.2. So it will come 130627.9. Now again P1 is equal to, it is also above to P4. So we'll just negate the height. So now the liquid here is water, right? Here liquid is water. So we'll take the density of water now. So P4 minus density of water GH1. So this is 130627.9 minus 1000 into 9.81 into 0.1. So this will come out to be approximately equal to 130 kilopascal. So this is option C. Okay. Let's move to next question. We have lots of interesting question today. So small gas bubbles form in soda when the bottle or the can is open. The average bubble diameter is 0.2. Estimate the pressure difference between the inside and outside of such a bubble. It is given that the surface tension is 0.0728 Newton per meter. Nothing to explain here. Simple formula will be suffice. So find this out, okay? Have you understood? All the values are given.
Option
Yeah.
A,
Option?
ma'am. A.
No, not option A. Just calculate that once more. You have missed something. It is a bubble, right? Not a liquid drop. You have missed something. Just think that.
Ma'am, will there be like two interfaces?
Yeah. Two interfaces will be there.
Okay, then it will be 2.91.
Done. Okay. So delta P is equal to 4 sigma by R. Simple. So 4 into 0.0728 and R is 0.1 into 10 to the power minus 3. It is a bubble. Like when it will be a drop, then we'll consider only one surface. So this is 2.91 kilopascal. Now for the next question. An atomizer forms water drop with a diameter of 10 in 10 to the power minus 5 meter. What is the pressure of the outside drop at 20 degrees Celsius if the pressure within the drop is 102 kilopascal? Assume the surface tension is 0.0728 Newton per meter. So water drop's diameter is given. And the pressure, it is asked to find if within the drop the pressure is 102 kilopascal. What is the surface tension? And surface tension is also given. What is the pressure outside the drop? It has been asked. So if this is the drop, surface tension will be this. and the pressure on the liquid side and pressure on the vapor side will be this. So PL will be greater than PV.
C, ma'am.
Yeah. So it's correct. So del P will be is equal to 2 sigma by R. So 2 into 0 0.0728, 5 into 10 to the power minus 5. So 2.91 kilopascal. Now we have been asked to find the pressure. So obviously from this diagram we can simply say that PL will be greater than PV. That means pressure inside will be greater than pressure outside. So Pi minus P naught will be the delta P. So this is equal to 2.91. So P naught will be Pi minus 2.91. So this is equal to 102 minus 2.91. That means 99.09 kilopascal. That means option C. Okay. Next question. Determine the contact angle theta if the liquid drop that is shown in the figure. Here sigma is the surface tension and subscripts. This is a simple Young's equation we have derived. No, we'll just use the same thing. So tell me what is the answer. We have already done this in the Young's equation.
Last option, ma'am.
Yeah. So this is very easy. We did it at the start. So sigma SL plus sigma LV cos theta is equal to sigma SV. So theta will be is equal to cos inverse sigma SV minus sigma SL upon sigma LV. Yeah, option B. Let's move to the next question now. Okay, which among the figure correctly represents the shape of the meniscus of the mercury inside a glass capillary? You already know this.
A, ma'am.
Yeah. So next question. Determine the excess pressure delta P in a cylindrical liquid jet over the pressure of surrounding atmosphere. Here sigma is surface tension and R is the radius of the jet. Determine the excess pressure in a cylindrical liquid jet over the pressure of the surrounding atmosphere.
C, ma'am.
Yeah. So it's very easy, like so if this is a jet, when it will be expanding, the radius will be like it will move to infinity. So R1 or R2, anything you can consider to be infinite. So delta P is the excess pressure. This is sigma 1 upon R1 plus 1 upon R2. So R1 if I take infinity, R2 will take smaller, that is the radius of the jet. It will start from radius of jet and will move towards infinity. So sigma 0 plus 1 by R. So delta P is equal to sigma by R. Next question. A vertical clean glass piezometer tube has inside diameter of 0.5 mm. What is the pressure applied water at 20 when a pressure applied water at 20 degrees Celsius rises into the tube to a height of 25 centimeter. So there is a clean glass piezometer tube and water is inside. So when the pressure is applied, water rises onto the tube to a height of 25 centimeter. It is given that the surface tension is 0.07 because it is water, surface tension will be this, and contact angle is 0 degree with the glass. Density of the water is 1000 and the acceleration due to gravity we have to take 9.8 meter per second square. So what is there are two questions. First one is determine the capillary rise in the tube. That means H we have to determine. So there are two pressures applied here, right? So initially there will be one capillary rise, and secondly there will be one excess pressure being applied, because of which the height have again changed to 25 centimeter. Like height have rise to 25 centimeter. So there are two pressures. So first initially we have to find the capillary rise. What will be the height because of capillary rise? And then we have to estimate the applied pressure. Can you do that? Have you understood or should I explain again?
We'll try, ma'am.
Okay. Understood, right?
Yes, ma'am.
Okay. Do it. Try, it's very easy. I'll just come back in 2 minutes. If you solve, then do tell me, okay?
First one, option A, ma'am.
Option A, yes. Second one,
Getting around 1869. Around option B.
B. Yeah, correct. Let's do it. Okay, so for the first case, we already know that capillary rise we'll find out as 2 sigma cos theta upon r. So this is 2 into 0.0728 into cos theta is 0 degree upon r is like rho g r, sorry. Rho g is there. So 1000 into 9.8 into r, what is given? 0.5 upon 2 into 10 to the power minus 2. So if we will solve it, we get 0.06 meters. For the next case, it is said that we have given they have given some extra pressure and it has traveled up to a height of 25 centimeters. So what is the pressure? So pressure difference we'll find out. So 0.025 meter for 0.0225 centimeter, right? So 0. Like 2 0.25 minus 0.06. So this is the pressure difference. So this is 0.19 meters. So we'll just convert it to the pressure. So rho gh is equal to, this is for water, is equal to the pressure difference. So delta P is equal to rho gh is equal to density 1000 into 9.8 into 0.19. That is the excess pressure. So this will be coming out to be 1862 Pascal. Okay, let's move to the next question now. A manometer is formed from glass tubing with uniform inside diameter 6.35 mm. That is, inside diameter is 6.35 mm for the manometer leg, as shown in the figure. The U tube is partially filled with water. It is partially filled with water, then it is filled with oil. And like volume of oil that has been added is 3.25 centimeter cube. Assume that both the legs of the U tube are open to atmosphere. That means pressure at point A and pressure at point C are similar, like equal. So tell me which of the options are, like for the first question, which among the following relationships are correct? Like for the first question on the left side is the first question. I've already told you this. One of them I told
Are
you.
are there two options here?
Yeah, two options are there.
PA equal to PC,
Hmm.
A and B.
A and
Second one.
yeah, correct. So one is there, the both of them are at atmosphere, so P and PC are same. Another for the same level, PB and PD are same. So second question is, which of the following expressions are correct? You can see in the second question, which of the expressions are correct? You tell me. You have to do the manometric balance, then you will understand.
Second one and fourth one.
Second one and fourth one, yes. So let us solve this one first. So PB is equal to PA, simple, the same thing that we did till now. Oil, GL. So PB minus PA is equal to rho oil GL. Next one is PD is equal to PC plus. PD is equal to PC plus that height L minus H. So that is filled with what? Water. So water G L minus H. So PD minus PC is equal to G L minus H. Next question. It is given that the specific gravity of the oil is 0.827. Then we need to find out what? We need to calculate the equilibrium height H. H we need to calculate, simple. So you have to do the manometric balance again. Okay, I'll wait for your answer. Then we'll proceed with the solution.
Third option.
Third option. Okay. Let's have a look. Yeah. So let's solve it. So it's given that rho g is equal to point. Oh, sorry. Okay. So we know that PB is equal to PD and PB is equal to PA. We have already derived this density of oil GL. This is another is PD is equal to PC plus density of water G into L minus H. So PA is equal to density of, so PA plus density of oil GL is equal to PC plus density of water GL plus H. Why? Because we already know that PD is equal to PB. So that's why we have just equated them. So but PA is equal to PC, right? So we'll just cancel them out. So density of G also will cancel. So it is density of oil into L is equal to density of water into L plus H. sorry, L minus H. Then L minus H is equal to density of oil GL upon density of water G. Okay. So the volume of the oil added is given as 3.25 centimeter cube, right? So this has been occupied in the whole volume, and what is the volume that is been added? If we will write in parametric options, so that will be pi by 4 d diameter of the manometer leg q, sorry, square, multiplied by the height which it has occupied, that is L. So this diameter is also given as 6.35 mm. So we'll take that in 1 unit. So pi by 4. So just 1 second. So this will be L is equal to 3.25 into 10. Though we are taking everything in mm. So pi by 4 into 6.35 whole square. So this is 102.62 mm. So in this equation, in the main equation, if you will put in this equation, if you will put this in this equation, so this will be H is equal to L minus density of oil G L, density of water G L. So density of oil multiplied G is 0.827 and this is 1. So 102.62 minus 0.827 into 102.62 upon 1. So this will come out to be 17.75 mm. So this is option C. So this question is done. Let's proceed to the next question. A manometer tube is filled with two type of liquids. Two type of liquid, 1 and 2. It's already given in the diagram. The density of liquid 1 is 0.8 and the density of liquid 2 is 1. So height is 10 centimeter, H1 is 10 centimeter. So what is the height H2? Very simple. We have already done this kind of questions. Okay. So I'll give you 2 minutes to solve this. I'll come back in 1 minute. So have you done the solution?
8 centimeter, ma'am.
Okay, yes. Okay, so we'll just take into the same level as we have already done. So this is 2, this is 1. So this is point A, and if we extend this only, this will be point B. So this is H1 and this is H2. So technically pressure at point A is equal to pressure at point B. So I've already told, like if the fluid is static inside a manometer, there is no other body forces, then we'll consider the pressure at the same level to be same. So H1 density 1 into G is equal to H2 density 2 into G. G will cancel out. So 10 into 0.8 is equal to H2 into 1. So this H2 is 8 centimeter. Okay. Next question. So we are doing a lot of problems on manometer. And even if it will be appearing for gate manometer questions, it will be there once. So in most of previous year question, you can find most of the year manometer question came only. So you won't stuck at any question. That's for sure. So the height of the water water in the manometer is 50 centimeters. And for another liquid is 30 centimeter. What is the density of another liquid? Solve this. Oh, hello. Am I audible?
Yes, ma'am.
Can you see the question? Right. I think I got disconnected. So
Yes, ma'am.
okay,
I can see the question.
okay. So you solve this question then. I'll be here.
$1,667.
Yeah. Same in the similar way, it will be density of water G into 50. We'll take both of them at the same point. Like if the midpoint is A, we'll consider it A. So unknown, this is unknown, G into 30. So density of unknown will be 1000 into 50 upon 30. So this will be 166.67 kg per meter cube. Okay. So and one more thing, you have not told the unit. You have to, if there is this subjective kind of question, keep the unit like always, because unit will take some marks.
Okay, ma'am.
So question number 14. Okay. So an oil of specific gravity 0.8 is flowing through a pipe. A differential manometer is connected at 2 points, let's say A and B, and shows the difference in mercury level as 20 centimeter. So what will be the difference between the pressure at those 2 points? Take density of mercury. Density of mercury is given, and acceleration due to gravity is also given. So it said that the mercury, like when the manometer is connected, the difference in mercury level was shown as 20 centimeter. So what will be the difference between the pressures at the 2 points? Okay, let's wait for 2 minutes, and if you'll solve before that, you can ping me.
25.6 kilopascal.
Yeah, you're solving very good. So we have just connected this manometer over here. Okay, so this is point A, this is point B, this is one fluid, and this is another fluid. So obviously at inlet the pressure will be high, so it will be more depressed. At outlet pressure will be low. That's why this, because of this pressure difference, like the fluid will be driving, right? So this is Y, this is mercury, and this is 27. And specific gravity of oil is given as point A. That means density of oil upon density of water is equal to point A. So density of oil is equal to zero point 0.8 into 1000. So that means 800. So now PA at point A plus density of oil at point A plus density of oil, and what is this height? This height is Y plus 20, right? So Y plus zero point 0.2 in meter into G is equal to at point B, pressure at point B plus density of oil into G into Y, plus for this density of oil into G into Y for this, cause this is oil here, uh, plus this portion is covered, this 20 centimeter is covered by mercury, so we'll take density for mercury there. So density of mercury G into 0.2. Now this will get cancelled. Density of oil Y, oh sorry, let me write it. PA minus PB is equal to density of oil GY, plus density mercury G zero point 0.2 minus density of oil G Y plus zero point 0.2. So this will get cancelled. This and this will get cancelled. So PA minus PB is equal to 13600 into 10 into zero point 0.2 minus 800 into 10 into 0.2. So this will be is equal to 25600 Newton per meter square is equal to 25.6 kilonewton per meter square. So this is option 1. Okay. Let's move to the next question. The left limb of the U-tube manometer containing mercury is connected to a pipe in which a fluid of specific gravity 1 is flowing as shown in the figure. Find the pressure of the fluid in the pipe. Take acceleration due to gravity as 9.81 meter per second square and density as 13600 kg per meter. So we have to find the pressure at this point. At the find the pressure of the fluid in the pipe. So the pipe is connected to one side. So we have to find the pressure at that point. And the point B, the other point, the other leg of the manometer is open to atmosphere. Uh, so you solve this, then we'll proceed with the solution. Ping me when I'm here only. You can tell me when you have solved. Okay, I'll come in 1 minute. Have you solved?
Second option, ma'am.
Okay. 15125 6. No, it is. It will be the correct option. Will be option number 4. Check once.
Is it gauge pressure or absolute pressure which we have to find, ma'am?
What?
Is it gauge pressure or absolute?
Absolute pressure you can find because I have not given you the atmospheric pressure.
Okay, I actually got the option 25898.4. Then I added atmospheric pressure to it. So I got option B.
Oh, no, no. Atmospheric pressure, you can't, you don't know the atmospheric pressure here. I have not given you. Because with height, the atmospheric pressure will change, no? So you can't attain. Like, as sir told you in the class about the story in the building. You take a
Yes.
barometer at the bottom and at the top. So once you will go at the top of the building, the atmospheric pressure will be different there.
Okay,
Okay.
ma'am. I assumed it as atmospheric, normal.
One atmosphere, I understand, but it won't get right. Okay. So
Okay.
let's solve this. PA plus 1000 into 9.81 into 0.08. So similar is similar, everything is similar here. 0.2. So this will be nothing but 25898.4. Okay, so we have three more questions left. Simple, rather simple questions, similar to kind of. So, question number 16, yes. The YouTube in the figure contains two liquid in static equilibrium. The water of the density 1000 is in right arm and oil of unknown density in the left arm. L is 80 and D is 20. Then density of, find the density of oil. Simple, similar only.
800.
Yes, it's very easy. So pressure at A, density of oil, G, D plus L is the length, like cos it is D plus L down. So is equal to P at point B. So B we are taking that second point. So plus density of water G. So this both of them are at atmospheric pressure. So this will be get cancelled out. So density of oil is equal to density of water GL upon G D plus L. So GG will cancel out. So if you will put everything, it will be 800 kg per meter. Okay. Next question. In an open U-tube containing mercury, kerosene of specific gravity of 0.8 is poured into one of the two lamps, so that the length of the column of kerosene is 40 centimeter. The level of the mercury column in that limb is lowered approximately by how much? Level is lowered approximately by how much? You take the initial level and then you see how much it is, like on the left arm it is lowered, it will be lower, then on the right arm it will be rise, right? So in that way you can do the pressure balance model. Okay, solve this.
2.35 centimeter.
How much?
2.35 centimeter.
No. No, it's not correct. Tell me how you have done. There must be some mistake.
Uh, when we add kerosene, then the other side of the limb, the mercury level will go up. So that height into density into
Uh,
gravity.
so if I take the initial height was h1, it will be rising by h1 again. Like if I take the rise, so it will be 2h1, no? Twice. Okay, let me do it. See, if I'll draw the diagram, it will be easier for you to understand. It is really good diagram now. Really unlikely. So this is A, and let's suppose this was the initial height, right? This dotted portion. Now, after pouring the kerosene, like it have depressed to here. It have depressed 40 centimeter. It have depressed 40 centimeter. So if this is H1, like initially H1 is what? Initially the height was H1 above, and now it is H1 below. So if it is H1 below, initially let's suppose it was here, right? At the same level because it was at equilibrium. So it would be at the same level. So now it has rise up to h1 height, right? So if I'll bring this also here, this will also be h1, and it has risen up to h1 height, right? Now if I'll do balance at point B and B dash, so this is plus 40. This one is kerosene, right? So 40 into G into density of kerosene is equal to P of B at point B. If I take this is PB and this is PA. So sorry, C. If I take this, because B already we have taken, right? So we have to take C. So P C plus. So this is the whole thing is there will be 2H1. 2H1, let's suppose if we consider as 2H1, 2H1 multiplied by G multiplied by density of mercury, that is Hg. So this will be getting cancelled out, this G will be getting cancelled out. So density of kerosene we know, mercury we know, so H1 we need. H1 is equal to 40 density of kerosene upon 2 into density of mercury. So density of kerosene is given as how much? Density of kerosene is given as, it is given as 800, and this is 13600. So this will come out, if you solve this, it will come out to be 1.17 centimeter. Not this one, 1.17 centimeter. So this is approximately equal to 1.2 centimeter. Did you solve it like this?
No, ma'am. I took the height as h1.
Height as h1, but it will be depressed also, na? So you have not taken both of them into consideration. Like this side will be depressed and this side will be increased. So we have to, if we want to match the level, it will be 2h1 at last, right?
Yes, ma'am.
Okay. Last question. A capillary tube of diameter 2 mm is dipped in a liquid of specific gravity 0.8. The liquid rises in the tube by 15 mm, making an angle of contact 0 with the tube. Determine the surface tension of the liquid in contact with the air and the glass tube. Simple. Seeing the what the formula we always use, we'll use that formula. Solve this. What will be the answer?
Option C, ma'am. 0.06 Newton per meter.
So this is 8 4 sigma cos theta rho GD. So this is 4 sigma theta is 0 degree. D obviously is given 0.002 and this is 9.81. This is 800 and H is given as 0.015. So sigma will come out to be 0.05 something 58 something. So we'll approximately take it to be 0.06. Yeah, Newton per meter unit is essential. So yeah, this is it for today. I'll meet you all next week. So I hope you'll join next week, same time.
Ma'am,
Yeah, yeah. Tell me.
can I ask assignment doubt, ma'am?
Yes, 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 sure.
Like assignment 2, ma'am. Like it has already been submitted also.
Okay,
One, like I have doubt in one question, ma'am. Like regarding the answer which they have mentioned.
okay, okay. Which question? Tell me. Like, let me open the question first. One
Week
second.
1 assignment, ma'am.
Week one assignment. I'll open SWAM portal. One second. Week one or week two?
One, ma'am. One.
Okay, just wait. Do you have the question? Can you share, or it will take one more minute to open? The internet connection is slow.
Shall I say the question, ma'am?
Yeah, yeah. Tell me. If it is a theoretical based question, then I can answer. But without.
Theoretical based, ma'am.
Okay, okay. Tell me.
The question was which among the following are incorrect statements?
Hmm.
The first statement is the Cauchy's theorem is basically a statement of linear momentum conservation.
Hmm.
Second statement is Cauchy's theorem is valid only in presence of a body couple on the fluid element.
Hmm.
Uh, Third question is Cauchy's theorem expresses the traction vector on any arbitrary plane in term of the corresponding stress tensor components.
Hmm.
And fourth option is all of the above. So which one is incorrect?
Mm, let
Uh,
me check it. I think body couple. Like, tell me second option once more.
the Cauchy's theorem is valid only in presence of body couple on fluid element.
Second one, I guess. Just 1 second. Let me check.
In the answer, they have given second one and first one, ma'am.
First one, I don't remember what you have said. First one.
That Cauchy's theorem is basically a statement of linear momentum conservation.
Yeah, that is true only, no?
Yes, ma'am. Regarding that, I got doubt, ma'am. So,
It will be true. Linear momentum conservation only. For that only we derive the Cauchy's theorem. Like when sir did the whole derivation. Do you remember?
yes, ma'am. He took that F is equal to ma.
Yeah, yeah, yeah. So it is the momentum conservation, like mass into acceleration.
Yes, ma'am.
So in if it is
Like
mass into acceleration, momentum means what? Mass into velocity. So velocity is involved over there.
Okay. Like in the assignment, they have also marked that option. That first one is also incorrect. So I got doubt.
Okay, then.
So it is valid in presence of like a body couple also. No? I mean, body couple or no body couple, it is valid. Cautious theorem.
Uh, uh, no body couple, sir. Sir, just one second. Let me. I don't remember accurately. So no body couple. It will be valid for no body couple.
Okay, ma'am. And one last doubt, ma'am, regarding the like same assignment.
Yes.
Uh, Regarding pressure, ma'am, on a triangular fluid element,
Hmm.
that Px is equal to Py is equal to and Pn is true for both moving as well as static fluid element. True or false?
No, pressure
They have
force
given it.
will be valid for all. Like it will be for moving or static as well. It will be there. Just when the fluid is in static position, so at that time the shear component won't be there, but normal component will anyhow be there, no? So pressure is normal component.
Okay, but where it is moving, will pressure be equal, ma'am? Because of
No,
shear
like
component.
we can see in the pipe also, like we can see like 1 manometer if we will place, there is difference in pressure. That's why the fluid is moving, right? If I take other body forces zero, like if I take gravitation to be zero, if it is horizontal, right? So because of the pressure difference only is moving. So pressure difference will anyhow be there on the fluid element. If
Okay,
it
they
is
have.
if it is static also, moving also, but when it is static, the shear force, that is when a is like rectangular component is there, a will move to a dash or b will you remember the diagram, like if this is the diagram, this it will move like this. So this is
Yes, ma'am.
shear force won't be there when it is static. Only the normal forces will be there. Sir, I've told in the previous class. Have you taken the class?
Yes, ma'am. Like when he was deriving that, I remember him not taking shear component into
Yeah,
picture.
in static shear component won't be there.
But in moving, it will be there, no, ma'am.
Moving will be there. That's why there will be continuous deformation. No, because of the shear component only.
That time
Continuous
pressure
deformation.
will not be same, no, ma'am, at the point.
Pressure will be there. It won't be same. Like there is pressure change. That's why only pressure. Like you remembered, sir did one derivation like. If this is a if this is a body, uh, if pressure here is p and this is dx, then it will be del p. At the point the pressure will be del p del x dx, right?
Yes,
So
ma'am.
there is change in pressure in a fluid element. Even it is static or it is moving, there will be change in pressure. That's why in a pipe, fluid flows there may be some other thing also, right? In fluid move when fluid is moving, the if they say that pressure is not changing along x direction, then we'll take it
No,
as
ma'am.
zero.
This is different question, ma'am. At a point,
Okay.
ma'am, that triangular place.
I don't understand. Like which one you are talking about? Like let me open the question first.
Question number 7, ma'am.
Okay. Yeah, question number 7. What about this?
In that
Which
question
of the
number
following
8,
pH
ma'am.
8, 7 to 8? Okay. If px is equal to py is equal to pn holds true for both px is equal to py is equal to pn. Hmm, just one second. Let me get back to the cause it is 2 classes back. Just one second, I'll tell you.
so slow.
Ma'am, or else next class also, ma'am. Like, if
No, no,
there
I'll
is.
tell you. Just give me 1 minute. Actually, my net is not working, very slow. I have also forgotten what's a taught. So I'll tell you just 1 second. So, okay, got it. What is it? Which among the following is correct statement? So, hmm. So it will be true. Hello?
Yes, ma'am.
It will be true.
Okay, ma'am. So even if there is like shear force acting on it, it will hold good.
Hmm. It will be true.
Okay, ma'am.
Okay. Then
Thank
we'll
you,
log
ma'am.
off for today. Okay. Okay. Join you next class.
Yes.
Okay.
Thank you, ma'am. Ma'am, take care of your health also.
It's okay. It will be getting better. Bye.
Yeah. Thank you, ma'am.